everyone, myself is Divya Bahal, Assistant Professor in Chemical Engineering Department at LJ Institute of Engineering and Technology. The subject that we are going to continue is Mass Transfer Operation 2. So moving forward with this lecture, we will study today about feed plate and feed line, right? So here in this distillation column, you can see that your feed plate divides your column into two parts, right? The trays which are above the feed plate, that section is known as rectifying section, where vapors are enriched. Okay, more volatile components are enriched here and sent to the top, from where vapor of column goes to your condenser and it is condensed and you get your top product, that is your distillate. And part of that liquid, it is sent back to the main column, that is your liquid. Now the feed plate and the plates below feed plate, that section is known as stripping section, where your less volatile component is enriched. It means your less volatile component is more pure here. So the liquid, okay, and the bottom product is what your liquid. It is sent to the reboiler, where again your your liquid is vaporized and it is sent back to the main column. So you can see that the boiler vapor, what is that? Your liquid which is again vaporized. And the part of it which is taken out, it is your bottom product. It is rich in less volatile component. So yes, the feed plate is what again? The plate on which feed is introduced in the column is called as feed plate. So as I told earlier also that your feed plate divides your column into two parts, enriching section and stripping section. So you can see that if you are counting the plates from top, that is 1 to n. So okay, so 1 to n plus 1 is what? That area is your enriching section. Whereas including the feed plate, okay, I am giving the notation m. Right, so I am giving the notation as m minus 1, m plus 1. Those are my plates which are present in my stripping section. Hence, moving forward, so here you can see that you are introducing your feed into the plate F. Okay, your tray F is what? That is your feed plate. Right, the above column, okay, the above area of the feed plate is your enriching section, whereas bottom part is your stripping section. So here you can say that the liquid which is coming, okay, your liquid L is what? Your liquid flow rate in enriching section. Similarly, vapor flow rate is what? V. Now from McCabe-Thiele assumption, we know that okay, vapor flow rate and liquid flow rate in all the plates of any section is constant. Here you can say that in stripping section, okay, L bar and V bar, what is those? Those are liquid flow rate and vapor flow rate. Okay. Similarly, for various plates in the stripping section, your liquid and vapor flow rate would be same. Here you can conclude that liquid flow rate in enriching and stripping section might be different. Similarly, vapor flow rate in enriching and stripping section again might be different. It totally depends on your feed condition. Okay, the flow rate of liquid and vapor in stripping and enriching section depends on the condition of feed which is entering the column. Okay, it totally depends on the condition of feed. Suppose in your enriching section you saw that your feed flow rate is what? Liquid flow rate is what? L, whereas vapor flow rate is V. But same is not the case for stripping section. Okay, so why is that? See, you are introducing the feed, so already some amount of liquid might be there. Now because feed is introduced, okay, it might be liquid also, vapor also. So of course it's but natural that now the flow rate will change. Okay, so we will see how it depends on the feed condition. So these are the types of feed condition which you have to deal. So your feed condition might be what? Cold liquid. Okay, cold liquid means the temperature of this feed is below the bubble point. It is not saturated, it is cold, right? Second is your saturated liquid. It means liquid at its bubble point. Okay, their solution, the mixture, it would be at its bubble point. Means little mole supplying of heat, it will convert into vapor. That is your saturated liquid at its bubble point, just on the verge of phase conversion. Third is your partially vaporized feed. Okay, liquid plus vapor mixture. Fourth is your saturated vapor. Saturated vapor means your feed is totally vapor, not a single drop of liquid is present. It means it is at its dew point. Slight cooling will result into its condensation. Okay, slight change in temperature or energy will result into phase change. Okay, same as saturated liquid. In saturated liquid, your liquid is on the verge of converting into vapor, whereas for saturated vapor, your vapors are on the verge of converting into liquid. Fifth kind of type of feed is superheated vapor. Superheated vapor means its temperature is above its dew point temperature. So let's see how condition of feed. Okay, it affects the liquid flow rate and vapor flow rate in enriching and stripping section. So first type of feed is your cold liquid. So here you can see that on your plate you are introducing your feed. It is cold. Okay, it means it is coming in form of liquid only. Now as it is cold, so what it will do, the vapors which are rising from stripping section, because the feed is cold, some part of vapors might be condensed back. It means the liquid flow rate now in stripping section is very high, because already from top your liquid is coming. Your feed is also cold liquid. Because of cold liquid, part of vapor is again condensed. Hence you can say that three streams are responsible for liquid flow rate into the stripping section. One is your original feed, second is your L, that is the liquid in the enriching section. Third liquid which is coming is from the condensation of your vapor in enriching section. So you can say that the liquid flow rate in stripping section is more than liquid flow rate in enriching section. Similarly, you can say for vapor also, V bar is what? Vapor flow rate in stripping section. But a part of vapors is condensed back. Hence the vapors in enriching section would be less. Thus we get V is less than V bar. Clear? Similarly, now second condition is your saturated liquid. Saturated liquid means it is already at its bubble point. So what will happen here? Your saturated liquid is there, okay, it is already at bubble point, but here condensation of vapor will not occur. Okay, condensation will not occur, hence your two streams are responsible for liquid flow rate in enriching section. One is the feed itself which is saturated, second the liquid coming from enriching section. Okay, hence L bar, the liquid flow rate in stripping section will be more than liquid flow rate in enriching section. Here vapor flow rate, there is no effect of feed on vapor flow rate, okay, because condensation is not happening. Hence the vapor which is coming from stripping section, that would again enter the enriching section and it would be unaltered. Hence V bar equal to V. Vapor flow rate is same in both the section. The third type of feed is your partially vaporized feed. Okay, means your feed is now mixture of liquid and vapor. Liquid and vapor both are present. So here you can say feed is coming, part of vapor is going up in the enriching section and part of liquid, it is going into the stripping section. Hence you can say that liquid flow rate in stripping section is more than liquid flow rate in enriching section, but vapor flow rate in enriching section is more than that in stripping section. You can see here two streams are responsible for liquid which is coming into stripping section. Okay, one the feed itself, okay, liquid in feed. Second, the liquid which is coming from enriching section. So you can see two liquid streams are responsible to make liquid flow rate in stripping section. Whereas talking about vapor, here you can say that in vapor two streams are coming. One, the feed itself, okay, part of vapor which is present in feed itself, that is going into the enriching section, and the vapor which is coming from stripping section, it is also going into enriching section. Hence, net result is what? That your L bar is more than L and your V is more than V bar. Fourth condition is your saturated vapor. Saturated vapor means your feed is what? It is pure vapor. So here you can see that for vapors in enriching section, two streams are there. One, the feed itself which is in vapor form. Okay, so V is what? Feed which is coming into as vapor into enriching section. Other stream is what? The vapors coming from stripping section. Okay, so here you can say that two streams are forming as vapor which is going into enriching section. Here you can see that the liquid stream is undisturbed. Okay, it is not disturbed. The liquid which is coming from enriching section, same is going into the stripping section. Hence, L equal to L bar. It means the flow rate of liquid in both enriching section and stripping section is same. Last type of feed condition is superheated vapor. So from figure you can say that you are introducing a superheated vapor. Now because it is superheated vapor means its temperature is more than dew point temperature, right? So because of that, the liquid which is coming from enriching section, a part of it instantly get vaporized. So here you can see that there are three vapor streams. Okay, one, the feed itself. Okay, your feed is what? It is already vapor. Okay, it is already superheated vapor. Now as it is superheated vapor, what it will do, it will vaporize the liquid which is coming from enriching section. The third is what? The vapors which are entering from stripping section and going to enriching section. Thus the net effect is what? Liquid flow rate decreases in stripping section, whereas vapor flow rate increases in enriching section. So in yeast, for all the kind of feed we can relate, you have to remember the conditions here. For cold liquid, what is L is more than L bar and V is less than V bar. L is what again? Liquid flow rate in enriching section. L bar is your liquid flow rate in stripping section. Be very clear with the notations which you are using. Okay. Similarly, V is what? Vapor flow rate in enriching section and V bar is vapor flow rate in stripping section. The next topic is about Q line. What is Q line? So as we saw, based on the condition of feed, okay, your liquid and vapor flow rate in enriching and stripping section may be different, may be same, right? So here we are introducing a new topic, a new factor, that is Q, okay? So to calculate the change in phase flow rates by introduction of feed, Q factor is introduced, okay? Here you can say that your Q is measure of thermal condition of feed. Now Q, okay, it is also defined as the number of moles of saturated liquid resulting in the stripping section for each mole of feed introduced. It is also defined as heat required to convert 1 mole of feed at its thermal condition to a saturated vapor to the molar heat of vaporization. The thermal condition of feed might be what? Cold liquid, saturated vapor, okay? Whatever the thermal condition your feed has. Mole of feed at its own thermal condition. We have to convert it into what? To saturated vapor. So the energy required to convert your feed into saturated vapor upon the molar heat of vaporization. So that is again your Q factor. So let's see, on the basis of heat definition, right? On the basis of heat, your Q is defined as energy to convert 1 mole of feed to saturated vapor upon molar latent heat of vaporization. Hence I can define that my Q is what? It is fraction of feed that is in liquid. Whereas 1 minus Q is what? Fraction of feed that is vapor. Here be very specific with the notation. Here you can see the example of a feed tray. Feed is entering into the feed tray. Liquid which is coming from enriching section, that is L. Whereas L bar is what? Liquid flow rate in stripping section. Similarly, V is what? Vapor flow rate in enriching section, and V bar is your vapor flow rate in stripping section. Now, feed is introduced here. So, Q is what? What does Q suggest? It suggests the thermal condition of your feed. Okay, what kind of feed you are introducing, whether it is cold liquid, saturated liquid, whatever it is. Okay, so here from example you can say that QF is what? It is the moles of liquid in feed going to the stripping section. When we define Q factor, okay, it is what? Moles of liquid which is going into the stripping section. Similarly, what is 1 minus QF? It is moles of vapor in the feed. Okay, for example, you can say that my feed is what? It is 10 kilomole per hour, suppose, and Q condition is given 0.3. It means so the moles of liquid present is what? 0.3 into 10 is equal to 3 kilomole per hour. So in my feed, liquid which is coming is 3 kilomole per hour. Now it will add with the liquid which is coming from enriching section. Hence you can say that the liquid flow rate which is now going into the stripping section after feed introduction, what is it? L bar is equal to L, that is liquid coming from enriching section, plus liquid which is present in the feed. Here 3 kilomole per hour, what is that? It will add with L. So hence your liquid flow rate in stripping section has now increased. Okay, it totally depends on the value of Q. Similarly, the vapor flow rate in rectifying section is what? So here we saw 1 minus QF, what is it? It is moles of vapor in the feed which goes into the enriching section. So similarly, the vapor flow rate in enriching section after feed introduction is what? V. V is what? Vapor flow rate in enriching section. So V bar is coming from down. Okay, so hence V equal to V bar, that is vapor flow rate in stripping section, plus vapor which is present in feed. Okay, so that way you can relate V is equal to V bar plus 1 minus Q into F, where your 1 minus Q into F is what? Moles of vapor in the feed. Move into the derivation part. The liquid flow in stripping section is what? L bar is equal to L plus QF. Hence I can represent my L bar minus L is equal to QF. Now talking about the vapor flow in rectifying section. So V is what? V is equal to V bar plus 1 minus Q into F. Thus V minus V bar is equal to what? 1 minus Q into F. Now overall material balance in upper section. That is in your rectifying section, okay? Total vapor is equal to liquid plus distillate. Now material balance of A, what we get? Vy is equal to Lx plus dxt, right? Similarly, overall material balance in lower section, that is in stripping section. V bar is equal to L bar minus W, okay? Now material balance of A, what we get? V bar into Y is equal to L bar x minus W xW. This is the final relationship which you obtain from the equations of stripping section and rectifying section, okay? But the overall material balance over the column, what is it? Fxf is equal to dxt plus wxw, okay? So substituting the value of V minus V bar and L minus L bar, you get the following equation. And so the final equation is what? Y is equal to minus q upon 1 minus qx plus xf upon 1 minus q. So this is the equation of your feed line. It is also called as Q-line equation. Now to know the point of intersection of feed line and diagonal, substitute y equal to x, okay, because at that point both the lines are intersecting. Thus, what is the coordinate which is the intersection point? It is xf xf. Thus you can say that the feed line passes through point, this is the coordinate, xf xf on 45-degree diagonal and has a slope of minus q upon 1 minus q. Now moving forward, let's study how your q value and slope are related, right? So from feed line equation, what is it? Y equal to minus q upon 1 minus q, x plus xf upon 1 minus q. So let's relate feed condition with the q value and the slope and its significance. So first kind of feed is what? Cold liquid. For cold liquid, what is your q? Q is more than 1. Okay, first of all, the significance is what? Q is more than 1. It means first of all you have to heat your cold liquid up to its saturated condition. After it is converted into saturated liquid, then and only then it will be converted into saturated vapor. So here slope is what? Minus q upon 1 minus q, which will result into positive slope. Second is your saturated liquid. Okay. It means Q is equal to 1. The significance is what? Now only that much amount of heat has to be supplied such that phase conversion occurs. Okay. Note down here the heat required would be what? Latent heat of vaporization. From saturated liquid to saturated vapor. Saturated liquid means it's already at its bubble point. Okay. Little bit of heat supply and it will get converted into vapor. Saturated vapor. Now your feed is partially vaporized. It means now the Q value, it will be from 0 to 1, between 0 to 1, okay, because some part of it is already vapor. You have to supply heat to only liquid part of your feed, right? So heating depends on the liquid content. So here also the slope would be what? 0 to 1, okay. If your feed is saturated vapor, it means the Q value is what? It is 0. The significance is that it is already saturated vapor. See, we discussed from the Q-line equation, okay, the Q-line definition, that energy to convert 1 mole of feed to saturated vapor upon the molar latent heat of vaporization. So what you have to do, you have to convert your feed to saturated vapor. Here you can see if your feed is already saturated vapor, it means now no heat has to be given. Hence Q equal to 0. Now Q equal to 0, it means your slope is what? It is 0, horizontal line, right? Whereas if your feed was saturated liquid, then your slope was what? Infinity. Infinity means on your x versus y graph, okay, you will get a vertical line. If last condition is your superheated vapor. For superheated vapor, Q is less than 0. It means here you have to extract the energy from the feed. Okay, it is already at superheated condition. Here you have to extract the heat such that from your superheated condition it comes to saturated condition. Okay, so hence your Q is what? Less than 0. Again, now what is slope? Simple, substitute the Q value. It is less than 0. Okay, hence your slope would be what? Negative. Now let's have a look into y versus x graph. So here you can see that this graph is plotted on the equilibrium curve of y and x, right? N is what? N coordinate is your point of intersection of your feed line and the diagonal. Okay, so the plotting is what? For the slope of q line. Okay, here the slope is what? Minus q upon 1 minus q. So let's see, a line where q is greater than 1, what is that? That is cold feed. So you can see the slope is positive. Okay, B is what? Saturated liquid. It means for its q value is what? Equal to 1. Hence you can see the vertical line is there. Slope is what? Infinity here. Right, we saw here. See, the slope is what? Vertical line, infinity. Similarly, for partially vaporized feed, u value is what? From between 0 to 1. Similarly, the slope will also range from 0 to 1. Okay. Fourth one is your saturated vapor. Q equal to 0. Hence, your slope is 0. E is your superheated vapor. Here you can see that your slope is negative. From this figure, you can see that at third stage, okay, all three lines are intersecting. It means that your feed is introduced on the third plate. Okay, so how you can find the feed tray location? The stage where your three lines intersect. Okay, so this way you can know the feed tray location from the graph. So that was for today's lecture. Thank you.